So let's consider another example of Lagrange multipliers. This time where the boundary is a circle. And consider what's going on conceptually with graphs. F of xy equals x squared plus 2x plus y squared plus 2y. The domain we're considering is everything inside the circle of radius 2 centered at the origin. So you could write that with set builder notation like this, where 4 is 2 squared. So this would be the closed disk of radius 2 centered at the origin. So there's D. In this case, this is a closed and bounded domain. Therefore, by the extreme value theorem, there is going to be a global maximum and global minimum, also known as absolute maximum and absolute minimum, which will either occur at critical points in the interior or it will occur along the boundary, just like in Calc 1, when you had closed intervals, the max and min occurred either at interior points, critical points in the interior where the derivative was 0, or at the endpoints. You had to check the endpoints too. This is just a generalization of that. Again, the derivatives are fairly simple in this case. 2x plus 2 for fx and fy is 2y plus 2. Don't you wish I would put this one on the test? Because it's easy to solve for x and y. X is going to be -1, y is going to be -1. The only critical point, there's one critical point. The one point that solves both of these equations simultaneously is -1, -1. This circle again has radius 2. So this critical point is somewhere in this ballpark, right in there somewhere. We can use the second derivatives to figure out if it's a max or a min or a saddle point. The mixed partials both end up being 0 in this case. And the discriminant, which is also the determinant of this matrix, is 2 times 2 minus 0 times 0, a constant, 4, which is positive. It's when it's negative that it's going to be a saddle point. So this is either a max or a min. The sign of the second derivatives, the pure second derivatives, the non-mixed ones, being positive means it's concave up in both directions, in fact, and will be a min. There's going to be a local min at the critical point, -1, -1. You also need the fact that fx is positive. These two things imply that. Might be a global min as well. You won't know until you also check the boundary. Let's use the Lagrange multipliers for that. So the gradient of f has components 2x plus 2, 2y plus 2. The g function is a function whose graph is the boundary effectively. It's that the equation of the boundary there is x squared plus y squared equals 4. For the g function, you can use x squared plus y squared if you want. You could also use x squared plus y squared minus 4 if you want. It doesn't matter. I'll use x squared plus y squared. The gradient of that is then going to be 2x, 2y. You're solving for where the gradient of f is a scalar multiple of the gradient of g. In other words, here's a conceptual point. You're looking for a scalar lambda where this is true, which means these vectors are parallel. Though lambda could be negative, and so they could point in the opposite direction. You're looking for where the gradient of g, which along this boundary G is, this boundary, this circle is really a level curve of G. It's where it equals 4. G increases as you move away from the origin. The gradient of G consists of vectors that look like this. They are perpendicular to the level curve for G, and they do point outward because G increases. The gradient vector is not constant, right? It changes as X and Y change. But this is 2 times the position vector of the point XY. They point directly away from the origin. Makes sense. It's a circle centered at the origin. Question now is, where is the gradient vector for F parallel to these? Where along this boundary? F is more complicated, has level curves that are more complicated. It's certainly hard to draw without technology what those level curves will look like. Let's do that. F of xy, x squared plus 2x plus y squared plus 2y. Grad F, if you like. So I'm thinking of the input as being, technically in Mathematica, when you use curly braces like this, it's called a list. Depending on how you use this, that list could be a point or it could be a vector. 2x plus 2, 2y plus 2. Enter that. Make a contour plot of F. Add more contours. Looks like a fairly simple function. These are circles evidently centered at the local min. Looks like the maximum is where it's lightest is going to be over here. Probably along the line y equals x. And the minimum, there's the local min there. That looks like it's also going to be the global min because you're going toward lighter regions as you move this way. Along the boundary, there's probably a local min there, though. It's not quite as low as here, though. As far as the gradient of F goes, can you put those gradient vectors in the picture? Yeah, I mean, it's a little tricky. And maybe what we want to do, and the reason I did this is to set it up to make an animation to put it inside manipulate. I'd like a parameter that'll allow me to use the mouse to move the point around and the gradient vector around. It's a little weird as well. You have to use something called locator to do that. I'm just telling you. I don't think I've ever told you this before. Copy and paste this syntax here. P represents the point I'm going to move around. This 1, 1 represents the starting point. It'll be at 1, 1. To actually see the point P should graph the point. Yeah, now I can move that point around. Make it bigger. Big red point. Maybe green to see it better. There we go. Unfortunately, it doesn't, the level curves are kind of not so smooth. That can be fixed. Performance goal. Arrow quality. Okay, now the level curves stay better, though the point doesn't move around as fast. A little bit of a delay. It's doing a lot of calculations, by the way, to make this graph, because contour plot takes a lot of calculations to make good graphs with contour plot. I'll also want to add the gradient vector. Okay, here we have the gradient. The fact that I'm putting the P, the point in that gradient right there, is why I did the curly braces here, because P really is a point. Okay, let me divide the gradient vector by 5, make it shorter. Okay, so what we see here is the gradient vector of F. So I move it around. It changes. This needs to be a P here. But no matter where you are, it's always perpendicular to the level curves. Points in the direction of fastest increase from dark to light. And it's parallel to the gradient vector of G along the boundary, just at 2 points over here and over here. Though it's pretty short over here, so you don't see it really. And Lagrange multipliers is finding those 2 points. Let's do it. The system of equations is going to be 2x plus 2 equals lambda times 2x. Looking at these two things. Then 2y plus 2 equals lambda times 2y. Then don't forget your constraint equation as well. X squared plus y squared equals 4. You got to use the 4 if you're going to be on the boundary. So you've done this. This should be simpler than most of the examples you've done. 2's cancel. This one, you're going to get something similar. Set those things equal to each other. X and Y, these equations are kind of symmetric. That's why X and Y are going to be the same in value. You're going to be on the line Y equals X here. Cross multiply. Rearrange. Say I want to solve for Y in terms of X. Those cancel. Yeah, actually, it's pretty simple. Yeah, Y equals X. Then use your constraint. Replace Y with X. Get 2x squared is 4, x squared is 2. X is plus or minus square root of 2. Use the fact that Y has to equal X to find 2 points on the boundary. That are the 2 points to check. Those 2 points are on the circle of radius 2. They both satisfy this equation here. X squared plus y squared in both cases is 2 plus 2 is 4. You would not want to mix up the signs here. You would not want to say square root of 2, negative square root of 2, or negative square root of 2, positive square root of 2, because y actually has to equal x, not plus or minus x. Anyway, so again, that's giving us these 2 points on the boundary. Then you check, if you want to be thorough about it, you check where the function, what the function values are at these points. F of -1, -1. It's going to be the global min. Its value is going to be +1 minus 2 plus +1 minus 2 is -2. F of negative square root of 2, negative square root of 2 is going to be bigger, slightly at least. We saw in the picture, you'll get +2 minus 2 root 2 plus 2 minus 2 root 2 is 4 minus 4 root 2, or 4 times 1 minus root 2. That'll be a negative number, but it'll be bigger than -2. About -1.66. And then f of positive root 2, plug it into there, get 2 plus 2 root 2 plus 2 plus root 2, 2 root 2 gives 4 plus 4 root 2, 4 times in parentheses 1 plus root 2. And that's going to be your global max value. About 9.66. If it's asking for global max or global min, it means values, these outputs. So this one's not a global max or a min. It is a local min along the boundary. If it's asking for where it occurs, you use the points. But you should be able to think conceptually as well in the test. Maybe I'm not ruling this out. I'm not guaranteeing I'll do this, but I'm not ruling it out. I'll put a purely graphical problem on the test with level curves, and you have to decide where the maximum occurs or something, and relate it to Lagrange multipliers related to the meaning of that equation. One more thing I want to show you here in this example, and that is, so, you also thought about these problems by thinking about the boundary itself and plugging into the function. For example, along the top boundary here, you could solve this equation for y as a function of x. Y would be square root of 4 minus x squared. And plug that in for y to get a function just of x and optimize it as a function of x. You've done that. I'm going to show you another way to do it. You can use polar coordinates. Here's another way to think of it. You can, in the formula for the function, which is up here, you could replace x with 2 cos theta and y with 2 sine theta. Why? Because that's effectively the polar coordinates of points along the boundary circle, centered at the origin with a radius of 2. As theta varies between 0 and 2 pi. Theta is an angular variable. That's a function of theta that you can plot as theta goes from 0 to 2 pi to see where the maxes and mins of that function are. And by what we've seen already, they should occur at pi over 4. And add pi to that, 5 pi over 4. Right there should be a maximum. Right there should be a minimum. But we're going to see this as an ordinary graph. I'm plotting an ordinary looking graph. The maximum is right here. The first coordinate is pi over 4. The minimum is right here. Second coordinate is pi over 4, or 5 pi over 4. If I take the derivative of this thing with respect to theta and solve for where that equals 0, yeah, I get pi over 4 as one answer. Pi over 4 plus, or negative 3 pi over 4 plus 2 pi would be 5 pi over 4. 2 pi is 8 pi over 4. 8 pi over 4 plus, or minus 3 pi over 4 would be 5 pi over 4. So this does include those answers. That's another way to think about it.